Welcome to this video on symmetry. So let's take a look at some of the attributes for symmetry. And we're first going to talk about line symmetry. And so it says a figure has symmetry or reflection symmetry if it can be reflected across a line so that the image coincides with the preimage. The line of reflection which is also called the axis of symmetry, divides the figure into two congruent halves. So take a look at this heart. You'll notice here on the right, it's exactly the same as on the left. So that heart has symmetry to it. So here it says to identify line symmetry. So we're just going to go ahead and figure out if it is symmetrical, if it can be split in half, and then if so, how many times. So if you take a look at this particular example, if you were to split this like so, that would be the same on both sides. You could also split it horizontally or diagonally. That's a total of 4, but then notice we can also split it through these parts here. And if we count the number of lines we just drew, it's 8. Now, it's kind of confusing to look at all those lines, but notice how many points that we have that are significant on here. So if we kind of work around here, so notice that I counted 8. Now, if I start going around here, I start counting more, and I'll have a total of 16. Well, half of 16 is 8. So the answer is yes, it does have symmetry. And all the lines and their number would be 8. Now if we take a look at this next example, you could cut it horizontally and you could cut it vertically, but we could not cut it diagonally. That's not going to map to itself. So in this case, the answer is yes, but there's just 2. This one, if we tried to start cutting this vertically, notice if you were to flip this over, does this side that I've colored look exactly the same as this side? Definitely not. So if I was to go ahead and try to do it horizontally rather than vertically, the question would be, does this top half look the same as the bottom half? And clearly, no, it does not. So in this case, the answer is just simply no. Now in the case of the B, once again, we draw a line and see if it's the same on both sides. So if I color this in on the right side, is that the same on the left? And the answer is no, it's not the same. But if I was to draw this horizontally through the middle and color this side here, you'll notice that if we flip that over, it would map to this bottom side. So the answer is yes. And in this case, we have one line of symmetry. Okay, so let's take a look at this one here. It can be cut horizontally, vertically. We could also cut it diagonally twice. Now you can't cut it through these points here because it won't map to itself. So in this particular case, I drew a total of 4 lines. And finally, we have here the state of Ohio flag. Now, with the exception of maybe some of the stars, which potentially may not be, if we were to draw a horizontal line like so, if I was to color this top part, you'll notice that it would fold down to meet the other part. So the answer is yes, and there's 1. Next, let's talk about rotational symmetry. So a figure has rotational, or you can say radial, symmetry if it can be rotated about a point by an angle greater than 0 and less than 360 degrees so that the image coincides with the preimage. The angle of rotation is the smallest angle through which a figure can be rotated. So the smallest to keep in mind. So if you take a look at this square, for instance, here, if we were to rotate this 90 degrees counterclockwise, it will map to itself. And I can go ahead and trace this and then prove that that can be the case. So you can see here, I mapped it to itself, 90 degrees. So that's going to be the angle of rotation. And I can do that more than once, of course. There's 3, and then 4, back to the original shape. So the number of times that the figure coincides with itself as it rotates through 360 degrees is called the order of rotational symmetry. The magnitude of symmetry which is just another name for the angle of rotation, that smallest angle, like over here was 90, is again the smallest angle through which a figure can be rotated so that it maps to itself. So here's how we compare these. The magnitude is equal to 360 degrees divided by the order. So here it says, state whether the figure has rotational symmetry. Just like in the last kind of problems that we had before, we're going to say yes or no. And if it is, we're going to find the center of symmetry, or the center of rotation, and then we're going to state the order and magnitude of symmetry. Okay, so I'm going to go ahead and copy this figure here. And now I'm going to go ahead and rotate it. So let's see here. So is it the same after 90? Definitely not. Let's see if I can go here to 180. Oh, it's close, but not quite. 270? No, all the way back to 360. So even though it appeared like it might have symmetry, it actually does not. So this is a no here. Now let's go ahead. I can just, once again, just copy this figure, just trace it real quickly. And then I can do some rotating. Well, that piece did not connect. Okay, I've got it connected now. So let's go ahead and rotate that. Okay, now, just move that a little bit. You'll notice that it does map to itself. And there it is there again. And there it is there. So the center of rotation in this particular case is going to be right there in the center of that figure. It's a little harder for me because I can't move it from exactly the center, but the answer is definitely yes. Now, notice that it went to itself once, 2, and then 3 times. So the order is equal to 3. The magnitude, or the angle, is going to be equal to 360 divided by 3, which is equal to 120 degrees. So every 120 degrees, it's going to map to itself. And notice if you add those 3 120s up, you get 360. Okay, let's take a look at this next figure. All right, so once again, I'll go ahead and trace this. I'll rotate it, so certainly not after 90, but let's see if we can get this one to work out here. So this one's, it's pretty close. I think that this, we should say that I maybe made a slight little error in my copying, so we're going to say yes. As we rotate it back to the original. I didn't do a perfect job of copying that, so we'll say yes here. We'll get a different color than yellow. And we had an order which was equal to 2, and then that means the magnitude is going to be equal to 180 degrees. Okay, let's take a look at this one here. Here we have clearly a parallelogram. Go ahead and rotate this. Boom. There it's the same. And back to itself. So the answer is yes there. Order of 2. And if it's order of 2, again, that magnitude must be equal to 180 degrees. All right, let's try this one out. So there it is to itself. And again. And again. Again, my picture's a little off, but it looks pretty good. Okay, so that one is a definite yes. There, you'll notice that it went to itself 4 times. And 360 divided by 4 is 90 degrees. Okay, let's go to this last one. Let's see if this maps to itself before I go around the full 360. No, it's not going to work. And then we're back to the original, so this is going to be a no. So here we can go ahead and do some more practice if you'd like. Describe the symmetry of each icon. Draw the lines of symmetry. If there's rotational symmetry, give the angle and order. So we can do both the reflectional symmetry and the rotational symmetry. So here, this yin-yang sign is definitely not going to have line symmetry. The question would be, does it have rotational symmetry? Well, if I was to go ahead and color in the parts here that are darker and then rotate this, we'll see that it's not going to map to itself. So you might say, well, that's it, but look how one side would be dark and one side would be light. They need to be exactly the same, and it's not the same. So this is going to be a no all the way around. Now this next one here, on the other hand, and just trace that whole figure. That's colored in. As I start to turn that, you'll see that it does map to itself there. And then the second time, third, and fourth time. So it does have rotational symmetry. What about line symmetry? If I was to draw a line, like so, you'll see it's the same on both sides. And that way. And diagonally. And finally this way as well. So we have both in this case. So for the line symmetry, we have 4 lines. Whoops, let me get that pen there. 4 lines of symmetry. And then for the rotational symmetry, we have an order, which is equal to 4, and a magnitude, which would be equal to 90 degrees, because 360 divided by 4 is 90. Okay, this next one, it's a little hard to see this next one, so let me go ahead and get this properly split up. Okay, so we got a pie here. This one's going to be a little tougher because I just freehanded this, but as we rotate this, you'll notice that it is coming back to itself pretty often. Okay, so the question is, then, it's certainly going to have line symmetry. And if we were to take out the pieces of the pie, let's say we just considered the pie itself as a whole, and it's been just cooked, but it hasn't been cut. This would have, because it's a circle, an infinite amount of lines of symmetry. We could cut these pieces any way we want, right? So we could keep cutting, and it'd just be an infinite amount of those. So it has infinite lines of symmetry. And the order here would also be infinite. We could turn this as much as we want, as little as we want, or as much as we want. So this, yes, it does have rotational symmetry, but it's going to, again, we're going to be talking about an infinite amount of times we could rotate that. So yes, it does have rotational symmetry and line symmetry, but of course, because it's a circle, it's infinite. So finally, let's talk a little bit about three-dimensional figures. So as we wrap this up, when we think about three-dimensional figures, a three-dimensional figure has plane symmetry. In other words, it can be cut through by a plane. So here's this plane right here being cutting through. See this here? It's cutting through this rectangular prism. And if the rectangular prism is the same on the left and the right, then it has plane symmetry. And you'll see that this does have exact that. It has two halves that are exactly the same. Then we have something here that's called rotational symmetry when we're talking about two-dimensional, but a three-dimensional figure has symmetry about an axis, or this is called axis symmetry. So we have plane symmetry and axis symmetry. If we can rotate a figure and it maps to itself. So if we were to stick, for instance, like a stick through this particular cylinder and rotate it around, it's going to map to itself. So let's take a look at these figures that aren't quite exactly the same. So here we have a square pyramid, and the reason it's a square pyramid is because the base here is a square. So I could definitely cut this figure with a plane. So if I was to come through here and cut this like this here, you'll notice that it's going to have two halves that are exactly the same. So this does have plane symmetry. Now, what about axis symmetry? If I was to take this and come down through here, could I spin this around? Would it map to itself? And the answer is yes. This bottom is a square. So it does have axis symmetry. So in this particular case, we're going to say that we have both. Now, the way that I was able to figure that out again is because I focused on the base. And the base here has lines of symmetry. And it also can be rotated around. If you look at this base, this is a little different shape. So let's go ahead and draw this. So it looks basically something like this. Not exactly. But would I be able to cut this in half? Well, sure, I could cut that in half. So it definitely has plane symmetry. But could I rotate this around and it map to itself? Well, let's just go ahead and try that. I'll just go ahead and do a quick outline here. And let's see if that maps to itself. Well, there it doesn't. Finally, it does after 360 degrees, but that's not going to work. So this does not have axis symmetry. It's just going to have plane symmetry. Now this next one here, I do have a rectangular base, but then I've got, so it sort of looks like an L shape to it. So I want to focus on this as my base. Now, could I cut this way? Well, no, I certainly could not cut that way and it'd be the same on the top and bottom, so that's not going to work. But could I, for instance, cut this figure like this? So in other words, I'm coming down through this with a knife, if you will. I'm cutting through that. Would that be the same on both sides? And the answer is yes. So that does have plane symmetry because I would have this side over here. Okay, so there's this, and we've got this outlined. You can kind of see this would be exactly the same as this side over here, so it has plane symmetry. But could I spin it around? So if you spun that around this way, for instance, you'd end up having this bottom edge pointing to the left. So no, it does not have axis symmetry. And this next figure is somewhat similar. So you have this triangle here on the front. Notice if I was to cut this through the middle, how that shape is exactly the same as my base. And so this one does have plane symmetry. But could I rotate it around? Well, I couldn't do that, because if I did that, this edge would be pointed over here to the left, or up, or down, and that's not going to work. So it just has plane symmetry. And here we have two figures that are pretty similar to each other. This one here is a cone. This one's a little different than a cone. So this one here, if I was to cut this right through the middle, and I had this shape over here, there's the base, is that the same on the left? And certainly it is. So this definitely has plane. Could I rotate it around? Well, of course, look at the base, it's a circle. So it has axis, and so this is a both situation. Now this next one, we've got kind of a weird base here. So you might even draw it something like this here. Oop, there we go. Something like that. Now, could I cut that down the middle? Is there any way to get that to be symmetrical? And the answer is no. But could I rotate this? So let's just test it out. And again, I just freehanded this. It may not be perfect. We just want to be approximate here. But you can see here, it's supposed to map to itself. I didn't do a great job, but it's supposed to. And so that has an order of 2. So as a result, this three-dimensional figure will also have axis symmetry. So the base has rotational symmetry. That means the whole three-dimensional figure has axis symmetry. Okay, that's a lesson on symmetry. Hope it really helps you. Have a great day. Bye.